Here's an example of a logical digital circuit. And the goal is to write, for example, a truth table. We want to understand what this circuit does. Now, the first thing is to note how many inputs are there for this circuit. We've got A, B, and C labeled, and X is the output. The first order of business is to write out the 8 possible sets of inputs. Here are all the possible inputs, and we would like to figure out what all the outputs are. There are several ways we can go about this. The most direct way, I suppose, would be to actually follow the currents. Imagine we have low voltage, low voltage, low voltage, and see what happens. And we could follow through each of the 8 cases. Let's do the first one. If there's low voltage here, then current is not flowing. So there's no current flowing here, there's no voltage drop, and this is 5 volts. So that's a high voltage, which means that there is a path to the ground here, so you do get current here. And current here means you get a voltage drop. If there's current flowing, that means that this wire is connected to the ground, to 0. So this is a 0, this is low voltage going into here. And since it's low voltage, current does not flow. And if current does not flow, there's no drop, so you're still at 5, and X is a 1. Similarly, we could go through the same reasoning. If A and B are zeros, nothing's flowing there. If nothing's flowing, it's 5 volts. Comes over here, so we know we have something flowing. It doesn't even matter what C is. We have something flowing, so this is 0, and then that gets flipped to a 1. If A is 0 and B is 1, if A is 0, you have no current. No current means this is 5 volts. This is a 1. If you have a 1, current is flowing, so you have a drop, so this is 0. And 0 here means no current is flowing, so there's no drop, so X is a 1. So it looks like that's going to continue to be the case if A or B is a 0. Because if you don't get current flowing there, that means you do get current flowing here, which means you don't get current flowing here and you will have a 1. So that's 6 cases done. Last 2. What if, finally, we do have current flowing? If current is flowing down this one, we have 0 here. So nothing's flowing through this transistor. So it all comes down to C. If C is 0, then we have no current flowing. So we have high voltage, and then we finally get a 0. So that's if C is a 0, we get a 0. But if C is a 1, then we still get a current. And if we get a current, that's a 0, and then this works out to be a 1. So there's our truth table for that. Now here's another way we could accomplish the same thing. First, let's look at it and write the logic expression. Big picture, what is this circuit doing? Now you may have noticed that I kept talking about current here, current here, current here, because there are 3 logic circuits. Each resistor is the head of a logic circuit. The question is, will current flow through that resistor or not? Because if it flows through the resistor, you get a voltage drop, and if it doesn't, you don't. If you have one transistor alone, that's a NOT circuit. If you have 2 transistors in series, that is a NAND circuit. And if you have 2 in parallel, that is a NOR. So we can simply write the output of this as being A NAND B. That becomes one of the inputs with C into a NOR circuit. And then finally the output of that is fed into a NOT. So we can simply place NOT in front of this. Now there are many ways to rewrite this. Let's see if we can find a way to simplify it. An N here could be brought out in front. We could have NOT, and then to highlight it, let's say NOT A NAND B or C. This NOT on the OR can come out there. When that happens, both of these cancel. So we've simplified it to A NAND B or C. Now A NAND B, again, this N here can be brought out front, but not of the entire thing, in front of this parentheses. So we get not acting on A and B, or C. Now, not acting on A and B, the trick called De Morgan's laws, if you have not A and B, that can be written as not A or not B. And then we have or C, and if you have the or, then you actually don't need the parentheses anymore. So not A or not B or C. And that would make it a 1. So lots of things would make it a 1, as we see. What wouldn't make it a 1? The only way you would not get a 1 would be if you had A, B, and not C. A, B, not C. That's the only way you end up with a 0. So that's the approach using logic expressions. Now, some ask, how do you draw the logic gate diagram? Well, since this symbol is an and this symbol is NAND, this symbol is NOR, because this symbol is OR, and a not all by itself, they put a little triangle there just to give something to put the circle on. So how can we build this statement? Well, we could simply say not A NAND B nor C. So the A NAND B, that's A NAND B. Now we had a nor C, and then we had a not in front of the whole thing. So you can kind of see that not cancels out, and we could have just written it as an or. A NAND B or C is actually easier to write. To put these all together, not A or not B or C, into a logic gate diagram, we would say not A, not B, or C. And there you have it. So clearly there's more than one way to write these logic gates, just as there's more than one way to write the logical expression. There's only one truth table for a given circuit. So I hope that example clarifies how you can analyze digital circuits. How do you create a logic statement or a logic gate diagram from a truth table? Well, let's take an example where we have 3 inputs. These are the 8 possible sets of inputs. And X, let's just pick something like 1, 1, 0, 0, 1, 0, 1, 0. How can we describe this in logic statements? We're looking for patterns. Now, 1, 1, 0, 0 is sort of a mini pattern. 1, 0, 1, 0 is sort of a mini pattern. So maybe we can work with that. I was looking to see if there was any overall thing, like if it was alternating 0, 1, 0, 1, 0, 1, 0, 1, or something close to that. That would have been what I'd grab. But since I don't see any overall pattern that runs through the whole thing, I'm just going to go for sort of half patterns here, because I listed these out in order. Let's see what that says, and let's see what that says. 1, 1, 0, 0. Let's compare it with each of our inputs. A is 0, 0, 0, 0, nothing there. B is 0, 0, 1, 1. And this is 1, 1, 0, 0. So this is simply not B in that case. What about this half? Doesn't match A, doesn't match B. It doesn't match C, but in fact it's exactly the opposite of C. So this right here is not C. So there are 2 things that could be happening. We could have not A and not B. Or we could have A and not C. And there we have it. Not A and not B. Or A and not C. there is a logical statement equivalent to this truth table. Can we simplify it? It doesn't actually look like there's a whole lot. If I had a bunch of nans and nors, I'd be trying to pull knots out front. If I had knots in front of groupings, I'd try to distribute them and see if I could cancel things. But that actually looks pretty simple as it is. So finally, how do we draw it? Not A and not B. Here's an and, not on both inputs. That's not A and not B. Or, here's an or, A and not C. A, not C, A and not C, or not A and not B. And there is the logic gate diagram. This is only one possible way of describing it. It's probably one of the simpler ones. Some of these expressions you could come up with half a dozen different diagrams easily. So you just want to see what you can do to simplify expressions first.